Hi everyone, and welcome back to my channel. First off, a massive thank you for the amazing feedback on my last video. I really didn't expect such a warm welcome, but I'm so glad you enjoyed it. I hope this one meets your expectations too. This time, I've tried to keep things shorter to speed up editing and get back to you more often. So, without further ado, let's get started. Last time we left off with the 8563A analyzer fully assembled but totally unresponsive to keyboard commands. I was stumped. What could be causing this? My first suspicion was the A2 controller board or the A3 interface board, especially since I didn't know what issues this analyzer had before it was dismantled. Looking at the error list, one error stood out. Error 201, a system error. According to the service manual, this error is related to hardware-firmware communication. So maybe two microprocessors might be struggling to communicate with each other. Could it be due to a faulty component? But before jumping to conclusions, I decided to check the schematic first. Maybe I just misplugged something and the fix will be simple. Let's take a closer look. Looking at the board layout, the keyboard cables connect here, at the connector G602. The schematic confirms it's labeled as the keyboard connector. Tracing the connections, I found that this connector links to the data bus on the interface board. The schematic even labels this section keyboard interface, so I'm definitely in the right place. Most of the signals go to a NOR gate, which is pulled high and triggers a KeyBD RPG IRQ for interrupt request when a key is pressed. Could this circuit be faulty, preventing the controller from detecting a key pressed? It leads to connector G401. I'll keep that in mind as I dig deeper. The other key component here is U604, a 74SC244 octal buffer, which converts keyboard lines to bus data lines, BD0 to BD7. I traced where the BD0 to BD7 lines go next and found U600, another octal buffer. Guess where it leads? Connector G401 again. I see many signals going to this connector, so I have to go back to the board layout. I see that this connector goes straight to the A2 controller board, so that's where I'll start my investigation. If you recall, in the last video I spent a lot of time double checking all connections before moving forward. Well, I took another close look at connector G401 on the A2 controller board, and guess what? It was misplugged. Looking back at the footage, I realized I could have spotted this earlier. My bad. I didn't film the male connector before fixing it. I was just too excited to see the analyzer working again. But here's what it looks like now. Two of the pins were severely bent. Even after reshaping them, you can see they are still not perfectly straight. Luckily, I didn't break the pins while fixing them, so I won't have to replace the wall connector, at least for now. Let's power the Spectrum analyzer back on. No error 201 this time. Moment of truth. Yes! This thing is finally behaving. This was a silly mistake. The instrument had been reassembled carelessly by the previous owner, and I didn't check every connection thoroughly either. From now on, I'll double check again every single one to avoid any more surprises like this. Now that the instrument is finally responsive, it's time to tackle the remaining issues. I've also brought back my trusted test setup to assist me on this task. Almost all HP gear. Let's get to work on this analyzer. First, I'll go through each error one by one to see if any stand out. Here's one that catches my eye. Error 336, 10 MHz reference. And it's the last error in the log, which likely means it was the first one recorded during startup. So let's dive into the analyzer's block diagram to figure this out. Here's a part of the simplified block diagram of the 8563A spectrum analyzer. While reviewing the 8560A service manual, I've come across something unexpected. Indeed, this version of the service manual is actually for a newer revision than the 8560A I dismantled, but it is also in line with the 8563A I'm currently rebuilding. In the 8563A manual, you notice the A16 cal oscillator mentioned, while it is gone in the 8560A service manual. Their functions are integrated into the A4 board, just as I suspected in the last video. Though I mentioned A3 instead of A4, sorry. The A21 Oven Control Crystal Oscillator, or OCXO, is standard on this model as confirmed by the datasheet. The 10 MHz signal feeds different clock for this analyzer, such as the cal oscillator generating the 10.7 MHz required for the final IF mixing. This 10.7 MHz is phase locked to the 10 MHz reference. It also passes through a PLL producing 600 MHz and 300 MHz signals, also phase locked to this 10 MHz reference. Let's have a look to a more precise block diagram. Finally, it locks the YTO oscillator's frequencies through the roller PLL and the offset PLL. Looking at the 8563A element locations, the A21 is tucked under the CRT. Speaking of the CRT, the 8560A manual shows that the A17 board has longer standoffs, which explains why I struggled to screw it back in. My A17 board standoffs are shorter as it was designed to accommodate the A16 board. Once this project is complete, I'll 3D model a custom spacer to compensate for the missing lengths. So let's have a look now to this oscillator. As you can see here, the A21 oscillator's power supply and control cable are located right here, while the 10 MHz signal runs underneath through the SMB connector. According to the service manual, the first step is to check the power supply. With a scale of 5 V per division, the control signal is spot on at 5 V. Now let's check the supply voltage. Almost 15 V, just as expected. Now measuring the oscillator output, no signal. Double checking the supply voltage and control signal again. Yeah, still okay. So at least the issue of the A21 oscillator is definitely not on the power side. Now I have my frequency counter here, and it has a 10 MHz output. I use it to test if the spectrum analyzer responds. The analyzer expects a signal of 0 dBm, but this one seems stronger. Maybe I forgot to switch back to no attenuation on the scope. That probably explains why. The signal I'm getting out of this frequency counter isn't perfect, but it's a solid 10 MHz, so it should work for a quick test. Now I connect my BNC to SMB adapter cable to the A15 A21 oscillator input and inject the 10 MHz signal from my frequency counter into the oscillator input. This will confirm whether the issues lies here. Let's do it starting the analyzer now. The startup behavior is different from what I observed till now and much faster. And this is a success. The typical noise floor of this harmonic mixing analyzer is back. I'm glad I found the issue, which is a dead oscillator. But honestly, I'm a bit disappointed. I was hoping the remaining parts in this instrument were still functional. Now I'm starting to doubt the other components too. Let's push it further. I'll try measuring a signal to see how the analyzer responds. I'll turn on my signal generator and apply a continuous 10 GHz signal with a 10 MHz span. Success again. This is the first time in a long while that this analyzer has actually measured something. What this means is that there are no major errors in the work I've done so far. The big oscillator is functioning correctly, and all the components are reinstalled and reconnected are working together as they should. Now I'm playing around with it. The first thing I noticed is the level. It's about 10 dB lower than expected. Testing at 1 GHz now. The weird shape of the signal is due to my faulty signal generator, where the first band, 10 MHz to 2.7 GHz, is unreliable. So, I can tell if the amplitude is accurate without my power meter, but I'll save that for later. But still, I'm happy. This project is finally moving in the right direction. So, I've ordered the used oscillator. While I wait for it to arrive, I'll tackle another issue. Here's something odd. From the moment this analyzer first booted up until now, I haven't heard the attenuator click even once. So I'm controlling the attenuator manually through the menu. Still no clicks. Here's my plan. I swap it with the attenuator from my 8560A as they are pin-to-pin compatible. Ah, did you hear that? As soon as I plugged in the 8560A's attenuator, it clicked. Let's try manually changing the attenuation again. There, another click. Now I need to crack open my faulty attenuator and figure out what's wrong inside. Okay, now that I've removed the side and upper cover, I can pull out the entire attenuator assembly to have a look at what's inside. Wait a minute, what is this? A sticker over one of the ICs. That's never a good sign. This IC might be faulty. Let's take a closer look under the microscope. Ah, now I see why I couldn't hear any clicks. The electronic board is completely disconnected from the solenoids. Instead of wasting time diagnosing this board, I reuse the electronic board from the 8560A's attenuator and check if the most critical part, the attenuator pads, are still functional. Let's do the swap. I've reassembled the attenuator and I've reconnected the ribbon cable to test its functionality. My first goal is to check if these attenuators, the solenoids, are finally clicking. And yes, the solenoids are working. Now let's put it back in the instrument and see if this cheap, faulty attenuator was worth the hassle or if it was a total loss. Testing it again. Not good. There's a weak signal on the screen now. Earlier, when I tested the 10 GHz signal, it was much stronger. Actually, it turns out the seller, or whoever tried to fix this attenuator before, had left it fixed at 0 dB attenuation, meaning it was basically in full pass-through mode. Now that the solenoids are working, adjusting the attenuation does change the signal strength instead of just the noise floor. Right now, only the 20 dB, 40 dB and 60 dB settings give a reasonable power reading, though not the correct one. But every time the 10 dB step is involved, the signal gets much weaker. That's definitely not right. So I need to open the attenuator's RF cover and inspect those resistor pads closely. Looks like this attenuator was a complete loss after all. But yeah, this one is on me. It was a gamble and I lost this round. No big deal though. I've still got the 8560A's attenuator as a backup, and my plan is to reuse its resistor pads, which are still in good shape. Now here's the catch. I can't just drop the 8560A's attenuator into this analyzer because their designs are different. The 8560A has a series capacitors for AC measurements and uses one 10 dB pad, one 20 dB pad and one 40 dB pad. The 8563A, on the other hand, has no series capacitor. It's for DC measurements only, and uses three 20 dB pads plus one 10 dB pad to achieve the same 70 dB attenuation range. So while the 8560A's pads are reusable, their compatibility is a bit limited. Still, it's worth a shot. But for now, I'll save the attenuator issue for the next video, because the new oscillator part is finally here. So let's unbox it. Here it is! This oscillator comes from a different version of the analyzer, the 8563E, but since they share the same model number, it should be a direct drop-in replacement. At first glance, it looks like identical to the one in my analyzer, except that the wires here are soldered directly to the pins. One interesting detail though, the outer shell of these oscillators appear to be welded to the base plate. So let me know in the comments, would you like me to crack it open and see what's inside? If this video hits 50 likes, I do a short teardown video of my faulty oscillator. Now, let's swap out the old one and install the new oscillator. Back to the RF side. First, I need to unscrew the old 821 oscillator. While identifying the three screws I had to remove, I noticed the trimming cover was missing. Maybe someone tried to kickstart the oscillation by tweaking the trimmer? At least it was a red flag from the start that something was wrong with this oscillator. But I totally missed it. By double checking if the new oscillator will fit, I can confirm the trimming cover is there as well. Let's remove those screws now. From the top side, I remove the CRT again to get an easy access to the 821 oscillator. I also had to take out the battery holder from the back just to reach the SMB connector. I later realized I didn't actually need to remove the CRT for this job. Maybe I should have double-checked the service manual first. And here it is. This old oscillator has more rectangular edges compared to the new one I received. Side by side, they look almost identical, so fitting the new one in place should be straightforward. While I'm here, I'm taking the chance to secure the YIG oscillator. Its mounting holes are right next to the power supply cover. Now I just need to reassemble everything before heading back to the RF section to screw the new oscillator in. Moment of truth. Before testing the analyzer, I'll quickly check the signal with my oscilloscope. Look at that. You can barely see it, but I'm getting a super clean 10 MHz sinusoidal waveform. Way better than what I got from the frequency counter. Let's plug it back into the analyzer and fire it up. A few errors are still popping out, but yes, there it is. The noise floor is back. One problem down. Let's take a quick look back at this wild journey so far. First off, I finally managed to get this stubborn attenuator clicking. But we are not out of the woods yet, because those resistor pads still need a closer look. Then, I swapped out the faulty A21 oscillator, which finally gave me a rock-solid 10 MHz reference, and that alone got the analyzer booting up on its own, just like it should. So for me, it's still a win. For the first time in forever, this HP8563A is actually doing what it was built for, analyzing signals. A huge thank you to you all for watching, liking and commenting. Your support is what motivates me to go further and keep documenting these repairs. So, if you enjoyed this rebuild story, don't forget to like this video, and if you haven't already, please consider to subscribe. Like said previously, if this video hits 50 likes, I'll do a full teardown of the dead oscillator. In the next video, I'm going to dive even deeper into this attenuator, and I also start the tedious process of recalibrating everything. Thanks again for watching, and I'll see you all very soon for the next chapter.